Metallic automotive colors represent one of the most complex and failure-sensitive systems in OEM coating operations. Unlike solid colors, metallic base coats derive their appearance not only from pigment chemistry, but from the three-dimensional orientation and spatial distribution of metallic flakes within a rapidly evolving liquid film. This makes metallic colors inherently sensitive to formulation, application, and environmental variability. At the most fundamental level, metallic appearance is governed by flake orientation. Aluminum or effect flakes act as microscopic mirrors. Their angle relative to the surface determines light reflection, brightness, flop, and color travel. Small deviations in orientation create visible differences between face, flop, and near-specular viewing angles. As a result, metallic colors amplify process inconsistencies that would be visually invisible in solid colors. During spray application, the base coat film initially exists in a highly mobile, solvent-rich state. In this phase, metallic flakes are influenced by gravity, surface tension gradients, shear relaxation, and convective flow. As solvent evaporates, viscosity increases, and these forces gradually freeze flake orientation into the final film structure. The challenge lies in controlling when and how this immobilization occurs. At the formulation level, solvent balance is the primary driver of metallic stability. Fast evaporating solvents increase early viscosity and restrict flake movement, often leading to poor flop, dull appearance, or mottling. Excessively slow solvent systems extend film openness, allowing flakes to reorient too long, increasing the risk of flooding, striping, and cloudiness. Achieving the correct evaporation profile requires precise tuning across multiple solvent fractions. Rheology design further complicates metallic control. Low shear viscosity and yield stress influence flake settling and mobility after application, while high shear viscosity controls atomization and initial flake distribution. If rheology collapses too quickly during flash-off, flakes freeze prematurely. If it remains too low for too long, gravitational and surface-driven flow distort orientation. Pigment, binder interactions also play a critical role. Inadequate wetting or poor dispersion efficiency increases flake interaction, promoting agglomeration and local orientation differences. These effects often manifest as patchiness or sparkle non-uniformity across large panels. At the process level, metallic base coats are extremely sensitive to spray parameters. Changes in atomization energy, spray distance, overlap, or gun angle alter droplet size distribution and impact velocity, which directly affect how flakes enter and spread within the wet film. Minor operator or robot deviations can produce measurable appearance shifts. Flash-off conditions are equally critical. Airflow, temperature, and humidity influence solvent evaporation rate and internal flow dynamics. Higher airflow can prematurely skin the surface, locking in poor orientation. Lower airflow may increase flow-induced defects and mottling. These effects are magnified on complex vehicle geometries, where airflow and gravity vectors vary continuously. The difference between laboratory panels and full vehicle bodies further exposes metallic instability. Flat panels provide uniform airflow, orientation, and thermal mass, enabling ideal flake alignment. Vehicle bodies introduce curvature, vertical surfaces, edges, and cavities, all of which disrupt solvent evaporation and flake mobility. A metallic base coat that appears stable in the lab may fail OEM appearance audits on full bodies. For OEMs, metallic failures present as color mismatch between panels, poor flop consistency, stripe patterns, mottling, or unacceptable sparkle distribution. These defects are among the most common causes of color rejection during launch and early production. RD&I teams therefore design metallic systems not for perfect alignment under ideal conditions, but for controlled flake orientation across realistic production variability. This includes solvent robustness, rheology stability, pigment dispersion control, and tolerance to spray and flash-off fluctuations. In summary, metallic colors are difficult to control because they depend on a narrow balance between solvent evaporation, rheology evolution, flake mobility, and application dynamics. Small shifts in any variable can produce visible appearance changes, making metallic basecoats one of the most demanding systems in automotive coatings engineering. If you have technical questions related to metallic flop control, mottling, striping, or OEM appearance failures, share them in the comments for discussion in future episodes.